So up to this point, we're still interested in the question how an individual's welfare changes when price change. There are several ways to measure that. The first one is to use the compensating variation. We talked about it last week. I will come back in a second. The second thing is the equivalent variation. So here's like the CV and here's the EV. And another measurement is to use the change in consumer surplus. Let's call it delta CS. Now, we already learned about the CV or compensating variation last week. That's the extra money we need to give a person in order to keep him or her as well as before the price change. So that's calculated as the difference in the expenditure needed to reach the same level of utility U0, the prior level. After and before the price change, right? So that means we take E1 minus E0. That's what we learned. How about the equivalent variation and the change in consumer surplus? We will spend the remaining time of this topic to talk about these two measures. Let's go. Okay. Again, with the compensating variation, we focus on the old utility level, U0, right? So now we could also turn around and look back from the new utility level, the U1. And that is the focus of the equivalent variation. So we could allow the individuals to move onto another indifferent curve and then let him or her ask the question, okay, so how much more or less I would have to pay to be as well off as now if the price were not to change, right? And that is, we talking about the new utility level U1 as the reference point now, but with the old price, PX0. One example, I love sweet potatoes. And as I told you last week, sweet potato is really cheap in Vietnam. And now that I'm in Germany, sweet potato is kind of luxurious good to me. It's so expensive in the supermarket. You might check it. And so my utility is reduced because of the sweet potatoes price shock. So it's reduced from U0 to U1. Then some days I wonder if the price had not changed, like the prices that I had in Vietnam at home, how much money would I have saved from my consumption level, like right now? Or to put it differently, I would love to pay to see the price of the sweet potatoes going back to the time I was still home, though I'm used to the utility level U1 already, and I don't need to get back to U0. So in that case, the equivalent variation will help answering my questions. Well, the example here is, I know it's not really precise because we're talking about a price change in a strict sense, that means the same location, but it's kind of something to help to understand the application. So the equivalent variation is, again, like the expenditure that you're spending right now, but with the new utility level already and new prices, minus the expenditure, the imagination expenditure that you would need to spend to reach your new utility level, but with the old price. That is its definition. So to refresh the graphical illustration of the price change on the utility maximization problem again, this is what we have. Suppose we have a consumer who maximized the utility level already at point A. Now, that is the initial utility maximizing point. Now, if the price of a good, let's say X, rises, the consumer will maximize the utility level at point C. Why? Because now the budget line moves back to the left-hand side, right? And the slope change, so that it has to tangent another new indifferent curve. In this case, it's also to the left of the original indifferent curve. That's what's happening that we know so far. So despite that we talk about the compensated demand for a while, and we will still talk about it, meaning we fixed a utility level. Still, this is what happens now. We move to another utility level when price change. Keep that in mind, will be useful later. Up to this point, we have two options to measure the impact of the change in PX. So either we keep the person on the same level of utility or welfare as before, U0, by compensating him with some extra expenditure. And this compensation is the compensating variation, right? Which is this part over here. An important point to note, though he or she is kept at the same utility level as before, the optimum point moves from A to B. Why? Because of the substitution effect, right? Or more technically, because when price of one would change, but the other remains the same, the slope of the budget line changes. Remember, so the tangent point with the indifferent curves has to change also. That's the reason. Second option, we can just let the individuals move on to the new optimum point at C with a new utility level U1. In this case is lower than U0. Now, and then we asked, okay, how much he or she needs to afford U1 if PX were not to change. So if price were the same as before, then the slope of the budget line stay the same, right? Consequently, this imaginary budget line now will be parallel to the original one, which is this one. Now, so they are parallel. Okay. And that implies that at point D, the optimum point for this budget line, the combination of X and Y will have exactly the same proportions as before, but just with different quantity, in this case, smaller quantity from that at A. Now, and again, because of the substitution effect, point D is different from point C. Okay? And this equivalent variation is this part here. Now, okay. So after being bothered with this super complicated concept, you might ask yourself, okay, why can't we just simply subtract U0 from U1? So we get something like delta U equals U1 minus U0. Easy, intuitive, right? Less complicated. However, there are two reasons why we cannot do that. The first one is, remember when we talk about the concept of utility, it has this ordinality property. So that means that only the ranking of the bundles or the baskets is important, not the absolute value of the utility. And we only interested in ranking if U1 larger than U0 or U0 larger than U1, but not the absolute difference. So this measure, first of all, not informative. The second reason, we also said that utility is a very subjective concept. It can't be compared across individuals with different utility functions, right? Now you know that utility can have many functional forms or preferences. So because of these two reasons, we cannot use this, and we have to come up with some monetary evaluations of the welfare change. And that's why it's a little bit complicated over here. Another thing worth recalling at this point is the Shephard's lemma that we just learned last week. So remember, we showed that the compensated demand function, for example, x, can be obtained by taking the derivative of the expenditure function with respect to px, right? Now we will make use of this result and the definition of the compensating variation to develop the last measurement of welfare change, which is the consumer surplus. At the end, you will see that it is actually a convenient way to use the consumer surplus rather than the compensating or the equivalent variation in many cases. But let's go first with some basic stuff using this result. Okay, this is the explanation for what's written on slide 14 about the relationship between the CV and the result of the Shephard's lemma. Now, so we have the definition of the compensating variation. I wrote it back here again, which is new expenditure at new price, but old utility minus old expenditure at old price and old utility. Okay. In mathematical terms, that is equivalent to the integrals of the derivative of the function e, the expenditure function, again, px, py, u, right, with respect to px. When px changes from px 0 to px 1, this is the integral. So why do we have to have this scary integrals? The intuition behind it is actually rather straightforward, and I think it would be good to share with you, and at least once in life we should understand a bit more about that, but you can skip it if you're not so much into it actually. No integral questions in the assignment, neither in the exam, I promise. So I show you why it is the case with this integral here. Now, so imagine we have a function e of a variable p, now, and then let's say equal fp, now, and then we have its derivative, which is the derivative of e with respect to p equals f prime p, right? Now let's draw a graph of this derivative. So here is p, and here is f prime, or e prime, right? Okay, so the derivative, let's say for example it looks like this. Now let's take a point where, for example, here we have px0. So by definition, the value of the function at this point is, so it's fx0. Let me write it here. So px0 of px0 is now a value which show how the original function change when px changes for a very small amount, very small amount px, evaluated at px0, right? Definition. So if px changes by this dpx amount, then this will be how e changes the whole thing. Now, okay, so that's the first thing. Keep that in mind. Now imagine we have a rectangle over here. Okay, I could actually draw this better with this color. Okay, with the width of the rectangle exactly this dpx. Let's put px here. Okay, exactly the amount of that change over here. So how do we calculate the area of this rectangle? By definition, this area will be dpx, the width or the length, now, times the height. So the height over here is the f prime px0, which is dE over dpx, right? And you can cancel out the dpx, at the end you have dE. So the very small changes in E. Now, keep that in mind. So, if we split the area here in many smaller rectangles with the same width dpx. So for example here we have another rectangle, and here another one. Now Okay, and then we calculate the area of each of these rectangles, and at the end we sum them up. What will happen? So every time when you calculate the area of each rectangles, you will get this DE. And at the end of the day, when you sum up all the areas here, you will get the sum of DE. Let's say here you stop it as PX1, now, which is the point here. So at the end, you will get the sum of the very small changes in E when PX run from PX0 to PX1, right? And that is exactly E1 minus E0. So that is why when you integrate the derivative of it over a range from px0 to px1, you get this compensating variation. Alright? That's the intuition behind integrals. So instead of like calculating the rectangle's area like for infinity numbers of rectangles, why? Because we want to keep the dpx as small as possible, so that these area above the curve as small as possible, the residuals as small as possible, so that the calculating of the area below the curve is more precise. So that's why dpx is very, very small changes, like we have said right from the beginning. Now, and there is a shortcut for calculating these areas of the rectangles, as it's called integrals. Now, why is a shortcut? Because with integrals, you could apply directly some rules without having to repeat that over and over and over again. So that is nice, even though I know that like it doesn't sound easy as it used to be in our earlier education. I know that. Alright. Back to the problem here. So when you're taking the integrals of this thing, thanks to Shephard's lemma, you could arrive in, so let's write it here, CV equals the part inside the integrals. Actually, what is that? The compensated demand function, right? So from px, sorry, I should have written over here px0 to px1, the compensated demand with respect to dpx. And this is what's written on your 14th slide. Back to the curve over here. So the derivative curves here that we talk about is actually the compensated demand curve. And we can integrate the area below this curve from px0 to px1 to get the CV. Okay, to sum up, when the price increases from px0 to px1, there will be a welfare loss for the consumers. And this welfare loss can be measured by the area below the compensated demand function and with x ranging from x0, sorry, with px ranging from px0 to px1. And notice that here, compared to what we had on the board, the vertical axis and the horizontal axis flipped. before that we have quantity on the vertical axis. So it actually doesn't change so much the concept, but just in case you're confused. I bet up to now you might get confused more than once. Okay, first place we said a price change involves both income and substitution effects, and the optimum point moved to another utility level, right? But then I turned to the compensated demand curves, which it only deals with the substitution effect and fixed utility levels. And then we have two utility levels, before and after, meaning two different compensated demand curves, right? One with U0 and one with U1. So at the end, which one to use? Have you wondered that yourself? So if you puzzled with such questions, you on the right track. Congratulations. It's indeed a problem that we want to overcome here with the consumer surplus concept. So let's go. Okay, let's put everything on the demand curve, right? You have price increases from px0 to px1 here. The actual market reaction will be moved from A to C. Market reaction means what we observe on the market, not like from individuals' behavior, but like the general reaction demand on the market. That's what we said before. We could only observe moving from A to C directly, okay? The consumer utility falls from U0 to U1, nothing new. And there we faced the choice of the compensated demand curve to use to evaluate the welfare loss, right? Now, if we focus on this demand curve, which has to do with the original utility level U0, then we actually talking about the compensating variation, right? So the compensating variation is CV equals PX1 BA PX0. So it's actually this area. All right. This is follow from previous slide. Now, on the other hand, if we focus on, let's change the color. If we focus on the compensated demand curve with new utility U1. Now, then we actually talk about the equivalent variation, which is PX1 CD PX0. So the area between the price change and below the new compensated demand function over here. Now, and you can see that they are different. How can we decide which one is more appropriate then? And this is exactly where the Marshallian demand kicks in as a middle way, a solution for our question. So let's say by construction, the Marshallian demand function over here must cross both A and C because these 2 points are utility maximizing points, right? One new and one old. Okay. So because it crossed, it basically split the area AB. Sorry, let's change the color. A, B, C, D into two approximately equal parts. That is A, B, C plus A, C, D, right? So to say, the area below the Marshallian demand function, which is now, sorry, should not be here, which is now this part. In between the two prices and below the Marshallian demand function, which is the Px1, C, A, Px0 is the average, somewhat an average of C is average CV and EV. So because of that, it's somehow a middle ground to avoid us to make the decision whether we should choose the new or the old compensated demand function for our analysis. However, not only because of that, because it saves us from making some choice, that we prefer it more than a compensated demand. Another important reason that we should keep in mind is empirically Marshallian demand, which has I, income, as an argument, is easier to observe than the compensated demand, which U as an argument. We already know that U is very abstract concept and hard to measure, right? So we could actually write the CV, and let me go ahead a bit and already call the area in between the two prices and below the Marshallian demand function as the delta CS, the change in consumer surplus, plus ABC, right? And the EV is the delta CS minus the ACD. So why are they differences? Why are there these differences, but not exactly the same? You can guess why. Because of the income effect. The Marshallian demand functions include both substitution and income effect, but the compensated demand only has the substitution effect. That's why the area is not the same. Now we can officially define the consumer surplus as the area below the Marshallian demand curve and above price. But wait, which price? The price we're talking about here is the price at which the utility is initially maximized. This is Px0 now. We start our analysis from there. So this is, as I said in the beginning, the third measurement of welfare change, which involves the Marshallian demand curve. So it shows how much an individual would be willing to pay for the right to make the transaction at this price. Okay, that's it for choice and demand. Congratulations for successfully completing it. I'm sure that even though it's tough, it's new, it's a lot of stress, but that will be helpful for you at least for the next part with the supply and production, and even further as you go along your master program.